It's my great pleasure to introduce our distinguished guest speaker for today's conference, Dr. Elizabeth Oday. Thank you, Elizabeth, to accept for speaking today. Dr. Elizabeth Oday is the CEO and founder of Olaris, the precision medicine company that leverage the Olaris toolbox, combining metabolomics, machine learning, and biology to uncover clinically impactful biomarkers that fundamentally change how diseases are treated and diagnosed. She is a true pioneer in her field. She served on the steering committee for the Scientific American Top 10 Emerging Technology Council and the World Economic Forum Global Biotechnology Council. She was co-chair of the Precision Medicine Initiative. Additionally, she is a board member of the Biological Magnetic Resonance Board and the Precision Medicine Coalition. And during her graduate and undergraduate studies, Dr. Oday received many of the most prestigious research awards. She earned her PhD from Harvard University, where she was a National Science Fellow, and her contribution have been widely recognized. She was honored as a change maker by the White House in 2016, a next generation leader in biotechnology by the Massachusetts Life Science Center in 2018, and one of the 90 women to watch by Women and Wealth magazine in 2019. So please join me in welcoming Dr. Elizabeth Oday today, who will be presenting on NMR-Metabolite biomarkers and clinical diagnostics. Thank you, Elizabeth, and you can share your screen.
Thank you so much for that generous introduction. I'm really humbled. Let me get my technology here organized. So, can you see my slides?
Not yet.
Let's see if this works. Okay.
Yes.
Something's happening, maybe?
Yes, something happening.
Perfect. Wonderful. Well, thank you guys so much for having me today. I'm truly honored to be here with you to tell you a little bit about what we do. And I'm hoping that this sort of excites potential partnership and collaboration opportunities. I will start with the only French word I know, which is bonjour. Thank you again for having me here today. So before I get started and tell you a little bit about what we're up to, I just did want to put my disclosures. As was sort of mentioned in the intro, I am the CEO of Olaris, where I receive equity and a salary, and I'm going to be telling you about our work today. And then I'm also an advisor and a short shareholder in different startup companies. So how I structured my talk today is that I thought it would be fun to tell you guys about the world's first non-uniform sampling NUS HSQC clinical diagnostic that we actually just launched on Monday. So this is an exciting week for us here. This is an assay that we call Olaris KTDX. It's a urine-based assay that can help kidney transplant patients kind of tell them what's going on. So I thought it'd be helpful and maybe fun for you to see, what that product is and what it can do. And then we'll sort of take a step back and show you kind of under the hood and the pipeline that we use to identify biomarkers and hopefully translate those into sort of clinical diagnostics. And as I alluded to, we love collaborating from academia to biopharma. I think, science comes from sharing good ideas and would love the opportunity to work with you guys. So before I jump in to show you the data, it needs to start with a huge acknowledgement and a thank you to the folks that you see here. This is the Olaris team. We are truly like a family. These are some of, the most incredible scientists and humans that walk the planet, and every day I really do feel grateful for the opportunity to work with these folks. So just very briefly, as was already mentioned in the intro, what's Olaris all about? We are a precision medicine company, or a precision diagnostic company that I started 10 years ago now, which feels both like a blink of an eye and so many lifetimes ago. I started it directly as a spin out from my PhD, which 10 years ago was perhaps not as in vogue as it is now. But the company has always been founded on three strong pillars of metabolomics, machine learning, and, I would say an expertise, but also a sincere respect for biology. And we've developed what we call the Olaris toolbox that sort of links insights from all of these pillars together to be able to develop diagnostics. I will tell you today about our first one, and in addition to sort of using the tech to build out our own diagnostic platform, we also work with others, to just uncover more insights into biology, right? And that could also be leveraging our technology to help accelerate drug development. So probably not necessary for this crowd, but the power of metabolomics. When I first started this company, people were always like, why metabolites? Like, precision medicine was just sort of taking off, but it was really focused upstream at like genetic or RNA-based or transcriptomic-based biomarkers. And I personally think every biomarker adds value. I am a fan of sequencing. I think it sort of should be default in the world, but that really just tells us what could happen, right? It's risk factor information. And as you sort of move down, the row here, you get closer and closer to phenotype. And, metabolites are often called the fingerprint of phenotype because they're a reflection of what is actually happening inside all of us. For us, we call metabolites any small molecule about 1,500 molecular weight and lower. That could be endogenous, that could be microbiome, that could be sort of xenobiotic. And by being able to sort of capture and measure the metabolites and link it back, with meaningful clinical insights, that's how we're developing our tools. And the company's sort of 10 years old, and we had to spend a lot of time, I would sort of say, fine-tuning the process of how, so metabolites have been known, honestly, since ancient Egyptian times, that they reveal interesting information about human health. They didn't know they were metabolites, but Egyptians knew that the smell or the color or the taste of urine relayed important information about human health. But metabolomics didn't take off like some of the other omics because they're really tricky, right? They're always changing. There's a lot of chemical diversity. There's no single platform can sort of measure them all. So we've been sort of painstakingly working through that process to develop a toolbox that lets us really tap into and confidently measure metabolites so that we can use that to drive precision medicine tools. And so while it's not quite as easy as 1, 2, 3, and then we get some glorious product, it is sort of at a high level organized in that way, where our process includes getting some sort of sample. To date, Olaris has worked on everything from blood, urine, cell lines, tumor extracts. We've done labeling of tumors and things like that, where we get some sort of sample, and then we pass it through both now our NMR as well as we have a mass spec platform at the company. To the best of our knowledge, we're the only company that leverages both technologies. And a big pillar or guiding principle at Olaris has been not just trying to detect everything, but trying to do it in a reproducible manner. So one of our mantras is reproducibility at scale. We've published sort of a lot on this, but for both our NMR and our mass spec technology, we really want to have trust and the biomarkers that we're seeing, and not just try to get a bazillion features, but then not know if they're real or there's some adduct or or something else like that. And so we've done a lot of work on this front end to get reliable data that then we can pass over to the AI or the machine learning side of the house, where I would say we do everything from really basic statistics of just what passes, a p-value and a fold change cutoff, to more customized machine learning, AI, and leveraging sort of our deep knowledge sets. We've done a lot of non-sexy work where we've looked at how do metabolites change with temperature, with freeze thaw, with sex, with diet. So all of that sort of helps us refine, metabolites that we might be measuring that at least appear to be different between, let's say, disease and healthy, or in the case that I'm going to show you today, kidney transplant patients who have a problem versus those that are not. And what that does is let us sort of just refine what we're looking at, and in every step of what we do, gain more confidence in the biomarkers that we're looking at. And then, again, a big pillar of Olaris is linked back to biology. I personally don't believe in black box AI, perhaps in anything, but certainly when it comes to science, medicine, or health, I actually think it's a disservice not to at least sort of dig in and try to see if there's, a potential mechanism that you might be able to be uncovering by trying to link, the differential metabolites that you see back to some, pathway, or at least let it pass some hypothesis of, okay, like that could make sense. And so we refine all of our signatures, through this process to ultimately get to the Olaris product, which is, a diagnostic to hopefully can drive clinical insights. And so our pipeline kind of goes from hypothesis to diagnostic. And in our case, we are talking about something called an LDT, a laboratory developed diagnostic. And so if you look at sort of the steps to say, like, okay, we think metabolites can do something, to we have something that we're now offering patients, what do you do? Right? What do you have to sort of fill in the gaps there? And so we have a process that includes, very robust quality control and SOPs that are at stage 1, so that when we actually do our discovery analysis or our proof of concept studies, the biomarkers there, we can already start to have really confidence that like they're robust and they're going to hold as we move forward. And then you have to go into more formalized analytical and clinical validation studies. These kind of always go back and forth as you're sort of refining things ultimately to get to sort of your final diagnostic. And again, this is never a linear process. As the company has continued to evolve and grow, what we learn is that as we move things forward, we could like improve our SOPs or include our inclusion or exclusion criteria, or we could know that there's some nuances that has to do with like sex or something like that, or we have to advise people that they need to fast before they give us a sample, otherwise the signature won't work, or things like that. And so this is a constantly evolving process, and we've built in sort of tools that now make this I would say a more efficient flywheel. So as I alluded, the company's 10 years old. Monday we launched our first clinical diagnostic. So it took us a while to get there, but now that this wheel, I would say, is in motion and we've developed all these learnings, we have, a timeline where we intend to, release a new commercial diagnostic like every 18 months, right? Because now we've got this thing sort of churning. So let me tell you about the first area that we're working on, and it's really about developing diagnostics that can completely transform the kidney transplant journey. So these numbers are for the US, but there's roughly about, almost 1 million people who are living in the US with end-stage renal disease. And at this point, that means your kidneys aren't working. So you have two options, get on dialysis or get a kidney transplant. Right now, the majority of people end up on dialysis, but this is not the end game that you want. Dialysis is honestly terrible. It costs billions of dollars, as well as less than 50% of people on dialysis will survive beyond 5 years. The far better option is getting a transplant. And so, many people move from dialysis to transplant, where, just quality of life as well as overall survival dramatically increases. But obviously, to get a transplant, that requires a donation. And, there's always more people on the wait list for a transplant than organs available. And so there are all kinds of cool technology and efforts about how do we expand the organ pool? How do we, perhaps take organs that, weren't the best criteria and potentially make them better? Or how do we even, I think, how do we maybe even take a step back and say, do we even have the right markers that know if the organs are fit for donation or not? And so there's a lot of exciting technology happening there. And then even more cool technology is also happening in the process of going from donor to recipient. Previously, and it still happens quite a lot, and it's crazy to me that all of this works. Everything I learned about here, I'm like, oh my God, wild. But typically during donation, the organ would be sort of harvested and then kind of just put in like a freezer or like a little ice box before it made its way to sort of the recipient. but there's been tremendous advances in things called EVMP, or ex vivo mechanical perfusion, where the organs are actually hooked up to these systems so they can start to sort of pump or pass blood through, or sort of pass fluids through before they get to the sort of the new recipient. And while there's still sort of a lot of unknowns have happened in there, there's a hope that this process actually could help be used to sort of recondition organs, again, expand the organ pool and get them more fit for the transplant. Because ultimately, we want people to be able to get these transplants and then go live happy, merry lives, dancing through the future. And Olaris is working on developing diagnostic tools across all of these lanes. We actually have been working in heart transplant, as I'm going to be showing most kidney work today, but our goal is to do this for across all of transplant. But we've had some sort of preliminary data already. It's actually a mass spec assay, and we're hoping to develop into some point of care solution where there's evidence that we might be able to have a metabolite-based biomarker that can predict what's called primary graft dysfunction. So right now, there's really no good way to tell people, like, look at the organ, or they might measure like lactate measures, and those are really just crude measurements. But there's no good really way to tell and predict sort of function of heart or function of an organ, and this is very true in heart, which is the work that we've done sort of to date. But we have a biomarker that at least seems to predict those longer term outcomes, which may also, again, expand that organ pool, but also set up the right support necessary so that if you have a more risky heart that could have a risk of developing sort of these graft dysfunctions, that you have like the tools and the resources in place to sort of minimize that. We've also, and we just published a paper, came out I think last week, about trying to sort of just look at what's happening during EVMP, ex vivo mechanical perfusion. So we published a paper again in heart, and our hope is to do it in additional organs like kidney, where when you take an organ and you hook it up to one of these machines, and you're passing blood through, or you're passing whatever, like what's happening during that process. And we started sort of mapping energy substrates to sort of see, is there something that one of these organs is really needs that's missing from that solution? And then perhaps you could, provide it back again to sort of promote allograft reconditioning, making more organs available. But the product I'm going to tell you about today is the one that is commercially available, and it's what happens post-transplant. So it's all about trying to sort of help transplant patients, just continue to live and, reduce some of the uncertainty in their care. So what our assay does, we call it Olaris KTdx, is it identifies grafts injury and guides clinical decisions. So the problem right now in transplant management is it's really hard to know what's going on. So patients have to take immunosuppressants for their entire lives to try to keep their immune system in sort of this Goldilocks, like perfectly balanced state. But it's really hard to know what the right dose of immunosuppressant is for any individual. And if you tip the scale in any one direction, that risks sort of severe consequences, where if you have too light of a dose of the drugs, then you're at risk for rejection and you're under immunosuppressed. This is becoming less of a problem these days because our drugs are so potent that people are, actually taking them at the cadence recommended. In many cases, this shouldn't happen, but a growing problem is the other side, where because these drugs are so powerful, we're seeing lots of instances of over-immunosuppression, where there's opportunistic infections. There's one particular case called pallomavirus-associated nephropathy, or PVAN, as well as increased complications like malignancy, cardiovascular disease, and others. And so right now, there's several very good biomarkers or diagnostics. The most well-known one is serum creatinine, that tells you you're fine. That like if your serum creatinine is, at a pretty low level, relative confidence that everything is okay. There's more advanced diagnostics like cell-free DNA, which do very sort of similar thing. They tell you you're okay, but there's nothing out there that can help you identify early graft injury so that you could hopefully sort of prevent some of the irreversible damage that happens as a consequence of these things. And so that's really like what Olaris sort of set out to do, is to see, can we uncover, using metabolites, a biomarker that helps for an individual patient know that like they're not okay, that the labs that you're seeing are quote unquote unstable, and that the doctor should do something. And the doctor's options right now are really to go order a biopsy and see under pathology, what's happening. Are you stable? Are you under, or are you over? And then based off of those results, perhaps adjust the immunosuppressant, the treatment. Ultimately, we want to maybe replace the biopsy because it's invasive and costly and has its own complications associated, where you could just hopefully develop a lab, that could just tell the doctor sort of what to do, right? Is the patient on the right dose? Fine, keep them where they're at, or do we need to make some sort of titrations? And I think where the field also wants to get is to be able to sort of regulate these immunosuppressant levels or tailor it for the individual. As I mentioned, over immunosuppression is a big problem. Transplant recipients are at a wildly increased rate for cancer and other complications that are due to sort of the chronic use of these drugs. And so what we're now working with some of our KOLs is, can we use our test, now that we have guardrails for what's like under and over, as you'll see, can we use that to sort of fine tune and get people to sort of the lowest dose of these drugs that sort of keeps them at the right level? So that was our hypothesis, is that we might have metabolites that could help guide those clinical decisions. And then we set out to do a proof of concept study to see if that was possible. So we worked with the University of Leuven in Belgium. As I mentioned, we love to collaborate across the globe. And we got 103 urine samples from kidney transplant patients 6 days to 164 days post-transplant. So this is just a sample map, like time map of where we got their samples. And every single one of these patients, we had a biopsy with them, so we knew exactly like what happened. So they were about balanced between, people who had biopsy-confirmed injury and people who had biopsy-confirmed stable grafts. On the injury side, they were sort of equally split between over immunosuppression, that PVAN, and under immunosuppression, which for us included both active rejection as borderline, as well as borderline rejection. And so this is just a little summary of sort of the patient characteristics comparing the injury group and the stable group. They're very similar, across, multiple metrics, age, sex, drug doses. The only thing that was significantly different between the groups is, as I mentioned, serum creatinine was slightly higher in the injury group, which is what you expect. But serum creatinine is not a great biomarker, because if you just use the serum creatinine levels from these patients and you try to build sort of a model to use like the serum creatinine value to separate people who have injury confirmed biopsy, which are going to be shown in all these waterfall plots in purple, versus people who have injury confirmed or have biopsy confirmed stable grafts, which are going to be shown in green, you can see that serum creatinine doesn't do a great job of separating this. And in this data set, you can see it has about 66% accuracy, which is in line with the literature that, sure, high serum creatinine does get some people with injury, but it unnecessarily would ding all these people in green here who have stable grafts, and it would also miss these guys sort of below the line. So there's a real need for a better non-invasive sort of biomarker to kind of go beyond serum creatinine. So what we did is we acquired both a 1D NOSI and 2D NUS HSQC for all of these patients. And we looked to find differential metabolites. This was our discovery analysis, and we found 7 metabolites that were significantly different between injury and stable. For us, significantly different means it passes both a p-value cutoff of 0.05 and a fold change cutoff of 1.5. That's our lowest level of significance. What we actually really try to strive for is things that pass the FDR fold change. As we all know, metabolites have a lot of variability with them, so setting very stringent cutoffs is sort of key. And 6 of the 7 of these differential metabolites also passed the FDR cutoff, which we were thrilled to sort of see. So then we built a heat map using sort of the levels of these metabolites and sort of did unsupervised clustering to see how they separated. I apologize, this is a little bit confusing because we did a lot of different comparisons, but if you look at the immediate top row to the metabolites here in the heat map, you see our purple and green sort of colors, where the expression of these alone, you separate many of the injury, from the stable. It's not perfect, but so we then sort of just checked that there was nothing else that could be sort of driving these signatures. We looked at whether it was the subtypes of injury. So PVAN is going to be shown in red, under and that's over. Blue would be under immunosuppression rejection, and again, green is always stable. Like that didn't seem to be separating it. There was no difference between males and females, which is the next row, and there was not really any difference between like when the time of the sample was collected. So the strongest sort of variable that we could associate with these metabolites expression was simply injury versus stable. So that made us feel good that, perhaps building a machine learning model using these features could be useful as to build a classifier. And indeed, that's what we did. So we separated the training data, those 102 or 103 patients, into a training and testing set. So it's tenfold cross-validation. And we passed the features through, and we built a series of different machine learning models from ElasticNet, OPLS, Random Forest, and others. And we evaluated them across accuracy, AUC, sensitivity, and specificity. What we like to see is exactly what happened here, that no matter what model you're using, that the numbers are, pretty kind of consistent, showing that those features, have good discriminatory power, and that's exactly what we saw. We also make sure that there's no potential signs of overfitting where any one of these metrics, between the training and the test cuts is significantly different, and it was not. We also do all kinds of feature selection and stress tests to sort of try to refine the signature. So this is just one example where we ran the Baruda feature selection model to see, if there was an ability to sort of reduce the sort of feature set, and there wasn't. But that led us to sort of build and select our champion model, which was this ElasticNet model here with an AUC of about 0.85, which we were excited about. So we then took that model and applied it and built the waterfall graph for those same 103 patients that I showed you their serum creatinine on the left, and now using, our signature that we call Olaris KTDX. And all of this is based off of this HSQC, metabolite signature. And so you can see just the, the wild improvement from where we started to where we are. So this was our training cohort. We then did it again in a validation cohort of about 43 patients. And again, you can just see the tremendous improvement from the standard of care of serum creatinine to what Olaris KTDX is up to. And now, not in here, but we've also now tested in over 680 patients from collaborations in Europe, in Korea, and in the US. And so we're excited about it. One thing was you're developing a diagnostics, so we can do all this cool research. It's like, oh, it's interesting, we're finding all this stuff, but what does it mean in the real world? And so you have to think about what's called CU, or clinical utility. And the way that you can sort of judge CU in diagnostics is thinking about metrics called PPV and NPV. So PPV means your positive predictive value, and your NPV is your negative predictive value. And so this is just, how often do I tell you there's a problem? Am I actually right compared to known truth? Or how often do I tell you you're fine? Are you actually fine? And in the world of transplant monitoring, these actually have different values depending on sort of the setting or the context of use. So when transplant patients are out sort of just living their lives, there's things called just routine monitoring or surveillance, where they'll go in every so often and get that serum creatinine test, right? And so in those situations, what you really want to have is, ideally the best test would have both high NPV and PPV, but you want things that can really help rule out injury, so that if you tell someone they're fine, that is the case. And so you can see Olaris KTDX in the surveillance setting has an NPV of 90%, which is higher than any other test out there, from serum creatinine to cell-free DNA. So if we tell you you're fine, chances are you're fine, and you can have confidence, that you're living the way that you should, and just continue sort of monitoring. Similarly, in the surveillance setting, while other diagnostics would fail to detect graft injury, we actually have the highest PPV of any test out there. So if again, somebody's living their life and everything looks okay, but the Olaris test says, hey, we might suspect there's some injury going on, that, doctors are really linking on that could have value, in part because our test, our under classification, includes subclinical rejection. So it's before, things are really going crazy. So the high PPV of our assay really has a lot of utility in situations where no other test is adding value, both to rule in injury through this high PPV, as well as to rule out injury through our high NPV. And the similar story happens in the indication setting, where now this is the situation where somebody's test has spiked. And like if you just use serum creatinine as example, serum creatinine is a very insensitive marker. It can change for a whole bunch of sort of different things, from stress to just like you moved around a lot more. And so doctors really don't know like what is the trigger that should cause a biopsy, right? So in our data set, there was a very small number of people who actually had an indication biopsy, but still we performed this PPV and NPV exercise. And you can see that in the indication setting, all these people, the doctor thought there was a problem, but our NPV is fantastic at 96%. So in the indication setting, if you're not sure if these, spikes in labs are meaningful and you run the Olaris test and we say like they're probably okay, that can help give you confidence that maybe you should just continue monitoring. Similarly, our PPV, I know it looks bad because it's 48%. That's driven by the low prevalence and the small sort of sample size that we're looking at. But in the indication setting, I think there's 11 indication biopsies associated with injury. We got 10 out of the 11 right. So the accuracy is actually quite high. And we're seeing that sort of play out as we do additional sort of data sets. So we are thrilled about that potential utility, but as we spoke and got feedback from both our physician as well as our patient partners, like, sure, it's great to know that somebody might be at risk at injury, but can you go one step further? Can you tell me like what type of injury it is? Because if you have under immunosuppression, the treatment is the exact opposite if you have over immunosuppression, right? So can we use metabolites to help guide and mitigate the risk of potentially giving a patient the wrong sort of treatment? And the answer is yes. We were actually able, using the training data and then the validation data, to build a signature with near sort of perfect accuracy to distinguish people with biopsy-proven PVAN from biopsy-proven borderline or active rejection. So what that has led to is this sort of two-step model where like we get a urine sample. We first say, hey, are you injured or stable? And then if we think you're injury, we can tell you which one. To the best of our knowledge, we are the only diagnostic or assay except for a biopsy that can let you do that. So it's pretty cool that a urine-based metabolite signature can match what is seen in the biopsy to reveal information about, the three most relevant clinical phenotypes in transplant of stable, under, and over. And this is just our performance and all of this in the training and the validation and in our combined data set. So you can see it's quite robust. So that's the product that we have launched, as I said, on Monday. This is the world's first in a couple of different ways, non-invasive diagnostic to detect and differentiate graft injury. But I'm also super proud from just the technical feat that we've accomplished, is because the assay is based off of an NUS HSQC sort of signature. And so how did we develop that, right? How did we go from the hypothesis of metabolite biomarkers can, identify injury and guide decisions to this cool product? It started with really robust quality control and SOPs. We recently published a paper that if you get a chance, I would highly recommend, that really just walks you through our entire pipeline of, over the years of what we've sort of seen is needed to really develop a robust and standardized urine-based metabolite profiling platform. So these are the steps, and I will briefly sort of walk you through them. But at a high level, I wanted to make the point is that, I think sometimes in research, and I remember it well in my, PhD days as well, of like, you feel the need to try to use all of the data and try to figure out a way to make things work. I think one of the biggest lessons I've learned, especially as you're developing diagnostics for, for patients and for people, is you have to know when to throw out bad data, right? We all know that adage, and it is very true: garbage in, garbage out. And so Olaris has really spent a lot of time developing these sort of QC steps at every step of our process, from it, in the lab to on the NMR to doing sort of statistical analysis, that just provides sort of stage gates of whether or not even we let a sample in for discovery or a sample in for sort of clinical testing. And one of the most, maybe the most critical steps is adjusting specific gravity. So SG, specific gravity, This is super key. In fact, I no longer really believe any urine-based metabolomic study unless they specifically address how they have managed specific gravity, because it's a big problem. So I'll walk you through this, but we do a specific gravity adjustment because it mitigates false positives associated with hydration. It makes our life easier for clustering across patient samples. And it also helps us set a good range of like what's a suitable sample where we can kind of trust the data. So specific gravity is sort of just a measurement of all the particles that are in sort of urine. It's a proxy for hydration. So if depending on the hydration of an individual, the level of metabolites in urine can vary sort of 15-fold through nothing from just how much someone has, been drinking. And there's diseases that also affect this as well. But it's a critical thing because it can wildly, bias you to think that you have something that's related to a disease, but it's actually just, a red herring due to sort of specific gravity. So the team has done some amazing work to just like test the influence of specific gravity in every way that you can imagine. So basically what we've done is a series of experiments where we take the same pooled urine at a defined specific gravity, and then we dilute it and we concentrate it a bunch, and we look at what happens and how do we like mitigate false positives associated with it. So one of the first things we did is just showcase the problem. So if you take these pooled urine, concentrated and diluted, and you did just normal NUS HSQC metabolite profiling here, just by eye, you can tell the number of peaks in the dilute sample is very different from the number of peaks in any of these more concentrated samples. So if I was going to run like a statistical test to find, features that are different between here and here, we're going to have a lot, but that has nothing to do with anything except this one is dilute and this one is concentrated. We did a series of both, I would say, manual creation and machine learning driven things to try to be able to say, is there a post-curative or a post-acquisition curative method to get rid of the false positives associated with specific gravity? And there is. So instead of doing like a traditional kind of 10x noise-based cutoff where you would like pick peaks and then feed that into sort of, your statistical analysis, what we've developed is something that we call the sum-based method, where it's similar to what people sort of do in mass spec, where we take a percent of the total sum of positive peaks, and we use that to sort of set our cutoff for peaks that we trust. And what you'll see by doing this, you dramatically reduce the number of false positives. And I just want to call out false positives in this are now things that pass not only just a simple p-value, but an FDR corrected p-value and a fold change cutoff, right? So if you're just doing sort of traditional noise-based cutoff and you haven't done something about SG, a lot of the hits you see, could be, not due to anything meaningful. So we were wildly encouraged that by using this new sort of sum-based thresholding that we can reduce a lot of these false positives. But it wasn't perfect. And what we noticed is that, the false positives sort of persisted even with these FDR cutoffs and fold change cutoffs, mostly when you were comparing like the most dilute to the most concentrated sort of samples. So we wondered, perhaps it's worth like just cleaning up the SG, right? Or getting things into like in the lab, doing, a pre-acquisition sort of cleanup to get things more aligned. And I'll jump ahead here for the sake of time and show you that, yeah, that actually is worth it. So first, if you look at the sort of table down the bottom, what we did in this experiment is we took concentrated and diluted samples and, just did the same sort of thing of compared them of this middle row of how many features would be statistically different across all of our metrics, KW fold change, FDR, and FDR fold change, but just comparing the high and the low, and you see tons sort of still pass. But if we take that same sort of sample we take a concentrated sample and then we re-dilute it to be within a specific range, and we've now done a bunch of tests to show what that range is, that you can completely eliminate these false positives, right? Especially at these higher sort of cutoffs of including both a fold change and an FDR sort of cutoff. So we were pleased to see that. And then what we also recognized that it had an additional sort of dual benefit is specific gravity influences your chemical shift. So this is just HSQC, same urine at all those different SGs that I showed you before. And what we saw is that there are, resonances that are sensitive to sort of SG, and this was independent of pH because we cleaned up for pH as well. And so if you're running clinical testing with thousands of samples, how do you know that, this peak and this peak are actually from the same metabolite because they're moving quite a lot? That's actually very challenging. And so what we saw is that if you actually, like, let's say, where is it, the concentrated one, take this green one, and then you dilute it to be within a particular range, you really get the chemical shifts to more align, which just makes your life easier and and gives you more confidence when you're doing clustering across, in our case now, we've got thousands of patient samples. So the next part of our process is navigator molecules, and I love these navigator molecules. We have two sets of navigators. The first one is a navigator molecule that just says, like, hey, did your prep go well? And then the other sets of navigators are more helping us inform kind of clustering and sort of next steps. So our process, I've said it now a bunch of times, we use NUS-HSQC. We're relying on the natural abundance of carbon, which means we need to concentrate our samples in order to be able to see anything in a clinically relevant time. So we have a lot of steps in our prep. We do a modified Fulch extraction to get rid of, proteins and lipids and macromolecules. We'll evaporate the methanol, then we lyophilize things, filter it, put it in an NMR tube, right? So there's a lot of different things here, and at any one of these steps, there could be potential sources of error or bias, especially when you have multiple people sort of doing this. So we wanted to develop molecules. Oh, my daughter has dance class in a sec. Molecules that could help us inform that, like, this all just went the way that we thought it would. After a long journey of testing out many different molecules, we identified 2-chloropyrimidine carboxylic acid as a molecule that could be really helpful. So we use this molecule now. We add it at the onset of sample prep. We have shown in numerous ways that it does not affect our metabolite spectra, the resonances for these molecules. This was one of the criteria. They're folded in our spectra, don't interfere with real metabolites. And we showed that the ratio of this thing that we now call NAV1 to DSS is pretty consistent from different days, different operators, unless you mess up. And so we purposefully messed up, let things sit, dropped things, did all these kind of fun experiments in the lab. And what it showed us is that if you ever have a NAV1 to DSS ratio of less than 0.08, you need to stop and go back and double check, did something happen in the lab? Because you might not be able to sort of trust that data. The next thing we have done is kind of like our NAV2 mixture, which includes DSS and DFTMP. So DSS, everybody knows, it's my favorite NMR reference tool. It's great, but it sticks to things, in particular proteins and lipids. We actually thought that could be a useful sort of thing where perhaps we could use it as a way to detect potential protein contamination or lipid contamination in our samples. So indeed, we showed that the DSS peak width was dependent as a function of protein concentration, and then just showing in our prep, if we forget or we leave out, the protein precipitation or the lipid precipitation step, that DSS peak width gets large. And so now this just becomes an additional sort of tool for us to say, hey, could there be something wrong with that sample? Does it have a lot of protein in it? Did, again, the prep not go well? And of course, DSS has the added value of also revealing how the quality of your shimming. And so in our SOPs, if we have a peak width less than or greater than 2, we try to re-optimize the shim. If it can't go there, again, then we go look, could there be something wrong with this sample? The other navigator that we use is actually built off the amazing work of Mike Riley, where he discovered this molecule called DFTMP, where he showed its 1D chemical shift is related to pH. We sort of confirmed that in our studies, and actually we're able to build a model that shows that we can use the DFTMP chemical shift to predict both the initial pH of the urine sample that went into our lab as well as the final sort of pH. And this is important, I think, as everybody knows, pH causes many chemical shifts to, move around. Even within the buffering capacity, we're using a very strong buffer, but you still get sort of slight shifts. And so it's really important to know what the final pH of your sample is, again, to make sure that you're having, high fidelity in your clustering. So this is a real example of 30 samples in Olaris. We've developed this thing called a cluster visualization tool, which just lets us see peaks across all of our samples. And we also now have this knowledge base where we know, okay, I'm in like a pH sensitive zone. These are 30 different samples. Their peaks are here. What we've done is kind of color coded them by like pH. And if you didn't know that the samples of these red ones and these green ones and these blue ones had a different pH, you might think these are different features. But we now are empowered to know like, oh, okay, these have different pH. I know I'm in the histidine sort of region. I suspect these are probably all histidine and should be, grouped together as one cluster. That is super important. And I often get asked the question, so I just threw in this slide at the last minute, like, should you clean up for pH? Because does it introduce false positives? What we saw is that the initial pH of your urine, if you take it like 5 versus 8, the most extreme case, and then you go through our whole method and then do statistical analysis to compare, metabolites in the low and high pH. Yes, there are things that would pass just a normal p-value cutoff, so it could introduce false positives if this is your threshold. But if you use more robust and more rigorous thresholds, you can sort of eliminate them. So in our case, we've decided that it's not worth cleaning up for pH for multiple reasons. One, it just adds more steps in the lab. But now, because we actually can use DFTMP to read out the pH of the sample, we can actually use that as a clinical variable because that information is in fact part of many diseases as well. So we have these navigator molecules that really just, again, give us both better control, quality control, and assurance as we pass sort of data sort of through. And so that's why when, we did that initial proof of concept study and we came up with those, 7 differential metabolites, I felt pretty good about them, that they have 6 out of the 7 passed the FDR, the other one was right on the border. And then we move forward with clinical validation and analytical validation as you're moving towards your diagnostic launch. And these can sort of be done in parallel. And again, there's a lot of back and forth. Clinical validation just means showing that it works in additional data sets, which is what we did. Analytical validation in the terms of diagnostics has really defined meanings. And so you basically have to show that your test, can fulfill these criteria, that it's precise, it's accurate, the measurement is linear, you have to define what your sensitivity is, and show the stability of your assay. And what's interesting is if you look at what's required to meet sort of analytical validation of diagnostic development, many of them have to do with like the test itself, right? It's just how good is our metabolic extraction and our NUS sort of measurement. The stability is more about the specific metabolites that you're measuring. And so we've now been through AV several times, and you can think about it like it basically works for all metabolites that go through sort of this process. And we're super excited about the results because one of the things that we showed is just how precise this whole pipeline is. So we had one operator prepare 22 samples a single day, and then we code all of our HSQ features by these X numbers. So this is one HSQC figure, and this is a feature, and this is another. And we looked at both a high SG and a low SG sample of like what the percent CV was for these features all within the same day. So somebody that's doing, all those steps in that prep that I showed you, and you can see the percent CV is quite tight. Then we did it between day precision where we had multiple operators across 20 days. And we looked again at the precision of these measurements. And I'll also say this included like helium fills and all kinds of things like happened in like weekends and holidays. And there was all kinds of stuff that happened in here. And still, the measurement is quite robust, which is exciting. And all the features in our HSQC and US measurements are now below 25%, which is our acceptance criteria. The other thing you have to show is that your measurements are linear. We've published on this previously using sort of model mixtures, and then we've now done it just in patient samples and shown that, yes, this feature X56, as you dilute it, that the NMR intensity decreases as a function of the dilution. And then the other thing that we have done is stability, and this is really now less about the measurement, but about the things, the analytes that you're looking at. And this informs your inclusion and exclusion criteria as you think about like launching a test. And so what we did is took urine, kept it at room temperature, ambient temperature at 4 degrees, or we took those extracted metabolites once they were on the NMR and just looked at like how their metabolite levels changed across, different time periods. And, this was really helpful for us because what we saw is that, after about 24 hours at room temperature, the metabolite levels are all pretty consistent, but then they start to go up. And this was very contrasted if you just kept things at 4 degrees, where things are pretty stable almost up to 14 days. So this has informed us that like our shipping criteria, like, okay, we really need to ship things on ice packs, and we can't accept samples that were collected greater than 24 hours because we won't really have line of sight of like what could have happened before we got the sample. And we know now that the metabolites are quite stable in the auto sampler, for at least a week. So that's how we've been sort of moving things forward, and what has led us now, to have the ability to launch the KTDX diagnostic. And at every step, just reiterating, we learn, we go back, and we iterate, and we seek to kind of constantly improve. One of the core values of Olaris, which we really do live and breathe every day, is always strive for better, and we're always looking for new ways to improve this. And so, that's where we are right now. We've launched this product. We're looking, for, to continue to roll it out and hopefully for it to have great impact. We are, working on these other ones, and I'll just briefly mention, as I said, we would love to collaborate with others. I think metabolites can add a lot of value in very different areas, and we've been fortunate to work with some amazing people, in Parkinson's disease and oncology and in rare disease, and would welcome the opportunity to work with you. So with that, I will pause and say thank you.
Thank you so much, Elizabeth, for this very interesting talk. We already have a few questions in the chat. The first is from Patrick Giraudot. Could you please tell us more about, first, how you automate the integration and processing of 2D NMR data? Is it a homemade software? And second, how you exploit the complementary between 1D and 2D datasets?
Yeah, so we have developed our own in-house software that let us go, from peak list to looking at these clusters and things like that. So there's some amazing people. I hope my pointer is being active here, but Chen, Jafong, and Jawan on our data team have helped us build these like visualization tools to help us go back and see how the clusters work. We can look at them across all of our patients, either all at once, or we can look at one at a time, which lets us, again, just develop the robustness in this. Everything is semi-automated because I really do think it's also important to have that expert look at it and check yep, that makes sense, right? So I think you get into trouble when you just try to click the button and then get the answer. So we've really been thoughtful about building those stage gates. And most of our signatures all utilize 2D because we want to figure out what the metabolites are and do that link back to biology. And so 1D just doesn't have the dispersion and the ability to really have confidence in those annotations that you get with the 2D. So most of our signatures and everything rely on the 2D. We heavily use the 1D though for QC, right? So NAV1 that we talked about, it's proton, AUC, we use the DSS AUC in there. As I talked about, DFTMP, we measure, in the 1D. So we use the 1D to kind of help us feel good about what we're seeing, and then move forward with the 2D.
Okay, thank you. Another question is from John. What is the minimum concentration range you could quantify for biomarkers by NUS HSQC in which amount of time? And maybe to complete this question, do you use also the absolute concentration of your metabolites as an entry for your analysis?
So the method is semi-quantitative. So start there and then work backward. And in our, let me see if I can just, In this paper we published in 2020, we've calculated like our LOD and our LOQ. So we do a 25% NUS HSQC Poisson graph distribution. I come from Gerhard Wagner's lab, so that's you know what Sven and helped pioneer. And so it's about a 1 hour HSQC. And in that time, we can see metabolites in the NMR tube that are like kind of in the low micromolar range. I think like if you look back at the paper, I think it's like 5 to 10 micromolar. And then of course higher. Now that's why we also do that prep I talked about where we're concentrating our things, you know, 5-fold. So the initial like concentration, I don't know, like jumping through slides here, of like what might be present in the patient's urine or the patient's, you know, we've done plasma as well, is probably like higher nanomolar, but that's kind of where we're at.
And maybe one last question. Could you please clarify if there are any specific sample preparation steps required to enhance the robustness of the method?
These on the screen, all of these. We've also tested like paramagnetic relaxation enhancement agents. We published on that. So you can add PRE, you know, so we've used gadolinium as an example that will improve some of your measurements. You know, it adds a couple more steps and some costs. So for our routine like workflow, we pretty much don't. So we really rely on kind of all these tips and tricks that are sort of here, right, of concentrating the sample. We use a 3 millimeter tube, we're using a cryo probe. But I would say, you know, the biggest thing to be able to enhance signal and be able to differentiate true signal from noise is this SG cleanup.
And sorry, we have time for one last question because I think it's important. I didn't see it before. Do you obtain the certification ISO 15189, or do you plan to get it soon? With this certification, Olaris will have the standard and capability of a medical testing lab under international standard requirements.
Yes.
Yeah, so this is a message from the president of the RFMF.
Oh, okay. Well, yes, it's pending. So right now we are a CLIA certified lab, which allows us to accept samples within the US, and we are kicking off CAP and ISO to support these next steps. You know, in particular because we collaborate with so many people, we want to be able, you know, to offer our services on a global footprint.
Thank you again, Elizabeth, for your talk and for answering all these questions. I think it's time now to move to our next speaker. Gildas Bertho works inside an interdisciplinary environment of research at Université Cité in France. He is working to promote NMR in human health projects for its transfer to a clinical environment. Since 2012, he supervises studies with hospitals to evidence the application of NMR-based metabolomics in clinical biology. Notably, he identified biomarkers of chronic kidney disease, explained recurrence of acute porphyria metabolites by the presence of key compounds, and invented a method to identify patients at high risk for bad clinical progression of lymphoma. And today, Gildas will talk about clinical screening and in vitro diagnostic research. So please go ahead, Gildas. You have the right to share your screen now.
Okay. Hello, everybody. Are you able to see my sharing?
Not in full screen mode, but yes.
Ah, okay. I have to do this, okay. So, I would like just to say that, you know, that in every hospital in France, at least we have a mass spectrometry well implemented. But for now, it it is not, NMR is not actually present in a lot of hospitals. It is the fact that NMR should be explored, but the application of NMR in a clinical point of view should be explored. So we are, I will explain now that NMR, as you know, it is not as sensitive than mass spectrometry, but it is a complementary technique, of course. And even a simple 1D NMR spectra can give you a lot of information in one go. And this high degree of complexity can be seen, for example, here in the urine sample. So clearly, we have a lot of information, and this can be useful for health application. And the way we use this information and extract this information is has been developed in two main ways. And from a spectral data information, you know that we are able to obtain with binning or bucketing technique the information about the amount of a compound here, for example, using the integration. But the problem of this technique is that if you have overlapping, it doesn't work well, and it is very difficult to really have a good quantification. So this is more or less what we have done before, as every academic people in this area are doing binning. But more recently, technologies like deconvolution techniques have been developed. So it is possible from a reference compound, reference library, to obtain a fitting, like for example for this compound here, on the true spectrum in gray, to obtain a better quantification. So this rather good quantification method needs a database, and most important, and it is the standardization. But it is costly, because if you have to do your own database to be sure that your fitting is good, it is rather quite time consuming. So my point of view, and it's that the key points to do good research in modern metabolomics in the clinical point for application is, first, have a large-scale study, of course, to have a good statistical relevance. This is very important in terms of health, of course. And the other is to have an established omics database. And most difficult and maybe the most important point is to agree upon standards. It's a key point, because you have to standardize your material and equipment to have a very robust and reproducible technique. So one of the technique which is proposed by the leader in the NMR provider is the IVDR. So IVDR means in vitro diagnosis for research. So this technology is for research. It's not for now really possible to apply it for a clinical application, but it is a way to test for us the real potential of this technique. So the key point, as I told you, is the sample preparation. So we have to agree to standard operating procedures like called SOPs to the way to prepare urine and blood. And you have to use the same material and equipment for every analysis. It means that you have to use same buffers, tubes, and automation should be tested. And of course, NMR spectrometer. So we regularly apply control quality to be sure that there is no deviation over time, and that we still have very good quality of measurement. So this technology IVDR is developed in the world with a network of platforms, and in the world we have. It is not a list of all systems, but you can see that you can find it at nearly every places, not in Africa for now, but it is interesting to know that in France, so Grenoble has the first IVDR technology in the platform Gemelli, which is implemented in a hospital. So with Paris in our lab, it is the second IVDR technology. So at Paris, what we do, we have been supported by the Région Île-de-France, CNRS, and INSERM to develop this platform called Paris Santé. So it has been recently inaugurated, quite recently in April 2021. So the advantages of this technology is that you have an absolute quantification, and so no need to separate compounds. And it is really, it's not true exactly, but it is more or less non-destructive. But most importantly, we have a minimal preparation. And it is highly reproducible because NMR is quite is known as a highly reproducible technology. And if you use standardized methods, you can try to do international studies because one sample will give the same results at any IVDR place. So you can do really international studies because the results will be not dependent of the platform. So this is what we are doing, and we have planned to use this technology for more than 10 years because of the stability of this NMR platform. So we can do long-term studies and follow-up, and also we are also able to do retrospective analysis. And thanks to a maximum of automation, we can do high-throughput scanning. So therefore, we have an overview on the metabolic status in the human body, and it is suitable, this technology, for the longitudinal study of large cohorts. So classically in NMR, we have two main workflows from an NMR spectrum. It is the oldest technology is mostly used by academics, as I told you, is to use untargeted approach, is that you bucket or bin the spectrum, and you can do chemometrics method with 1D univariate and multivariate analysis. But what we have with a targeted analysis, like with an IVDR technology, we have a quantification, and this quantification of a few compounds, the main one, gives you a report. It is a report called IVDR report. And from this IVDR report, you can do statistical analysis with uni and multivariate analysis, integrate the clinical data of patients, and therefore make interpretation with, of course, a close collaboration with physicians. In urine, you have a report. For example, we give up to 150 metabolites in a few minutes. And even if you can detect more, it is possible after to have a look at the results, because this measurement, you know, is very stable. It means that your platform is very stable. So you can have a look at the concentration of other compounds which are not targeted. But you have clearly a report, and every compound gives you have a value of the compound in terms of concentration relative to more or less normal value. And it has been shown that this technology can be is very efficient to detect inherited errors of metabolism. About blood, what we can obtain is two profiles. Because in blood, as you can see here, it is a 1D, classical 1D spectrum of blood. You have the main peaks here are coming from the lipoproteome and lipoprotein. So it is the assembly of lipids and apolipoprotein. And this complex lipoprotein have different size and density. And it is possible by NMR to differentiate a very large density lipoprotein from a high density lipoprotein. So this is one report that we could have. And the second one is, of course, the metabolic profiles with small metabolites, which are thin peaks here that you can see. So these two reports are very interesting and complementary, of course, because lipoprotein report is essential, for example, in a lot of diseases like the cardiovascular risk and this kind of disease. And for a metabolite report, you can see, for example, here for alanine that you have a fitting in blue, which is perfect regarding to the pink line here due to the real spectrum in black. So you have a nice fitting and you are confident about the value that you have in your report. And for lipoproteins, it is important to know that using NMR, we have access to much more parameters than in the biological lab, where classically you have total cholesterol, triglycerides, HDL cholesterol, and LDL cholesterol. So this is important to know that you have, of course, these 4 parameters in by NMR, but you have much more parameters like apolipoprotein A1, A2, B100, and combinations of parameters coming from, for example, triglyceride in LDL, cholesterol in LDL 1, 2, or 6, etc. So because we have a very nice subclassification of LDL into 6 groups, unlike VLDL and 4 for HDL. So you can have access to cholesterol, free cholesterol, phospholipids in these different particles, APO, A1, A2, and B100. So this is truly, this is important to know that it is new parameters, and this is interesting for clinicians because they don't have access to these parameters, basically. And of course, you have access to metabolites, and these metabolites can be also relevant. And if you use a DTA as the complexation agent, you have access to calcium and potassium concentration. So what we are doing at Université Paris-Cité, we are doing a longitudinal follow-up. We're studying cohort. We make a patient stratification, and we try to find biomarkers of diagnostic or prognosis for a disease. And we monitor also the efficiency of treatments. So our projects are from the newborn to adult, and we can notably say that we participate in post-acute COVID-19 studies and environmental exposition, and particularly the endocrine perturbators. So among these examples, I will talk about the first study we have done on VIVDR to show you what is the potential of this technology in the case of lymphoma, which is blood cancer. And the most common aggressive lymphoma is the DLBCL, so it's diffuse large BCL lymphoma. This DLBCL lymphoma, we know that although its treatment outcome has improved, 40% of patients will be refractory or relapse and die upon first-line therapy. So the aim of the study was to early detect patients at high risk of death and or relapse. So it is really a true situation. We wanted to test the potential of this technique in this hard problem. So in collaboration with Véronique Beau at the Faculty of Pharmacy and Catherine Thibault at Hôpital Saint-Louis, we have made this study and with LISA, which is the Lymphoma Study Association. It's an international multi-center study with a cohort remark. And what we have collected blood samples at diagnosis of lymphoma before first-line therapy, so before any intervention on the any treatment, to know if it is possible to detect this high-risk patient of death and relapse. So maybe you are not familiar with this kind of analysis, but it is called the Kaplan-Meier curves. So if we look at the overall survival, which gives you an evolution of the probability of survival of a population over time, of course it decreases. But if we look at the International Scoring Index, which is known as IPI for every oncolog, it is known as the reference. for diagnosis of high-risk population. And it is, as you can see, high-risk patients can be found, but it is not found early. It is very difficult, and the p-value is not very good. And if we use NMR, what we have found, it is confidential, but I cannot show you the biomarkers, but we have found an NMR-based scoring where we can find, as you can see, this impressive result because we are able to find high-risk patients very early. And it is very significant difference between this high-risk and other patients. And regarding to the relapse, what we can do with the profile-free survival curves, and regarding to the IPI, International Scoring Index, one can see that it is impossible to detect this high-risk patient. And you can see it is not at all relevant. And now, if you look at this NMR-based scoring, we detect all patients at high risk, nearly all. I mean, they're all deaf in fast. So, and we can rapidly detect early these biomarkers. So this is a very impressive result for us, and for us it means that this is the first time we can see that NMR can be applied to find for a cancer these high-risk patients. So it is in collaboration with our colleagues at Saint-Louis and the LISA. But we also collaborate inside the consortium. We are located in the middle of Paris, and you can see that we work with a few hospitals at Paris, but not only, and with national studies like Constance cohort, which is related to the long COVID syndrome, and the international studies also with Sweden, Canada, Cameroon. And I would like to warmly thank Nicolas Giraud, which is our team manager, and Cédric, which are essential for these studies, and all the team of NMR and biological substances for their help for this kind of results. And I would like to thank you to RFMF Junior for the invitation, and you, of course, for your attention.
Thank you so much, Gildas, for this really nice presentation. Just there are two questions in the chat, so I will quickly ask for these two questions, and then we will go further on the webinar because we are a little bit late. So, but the first question is about the pre-analytical step and the choice of the plasma anticoagulant. Sorry, the choice of the anticoagulant, yes, for the plasma. So, do you think heparin or EDTA samples, EDTA plasma, which one is the best one to make NMR studies, and what about the minimum volume required?
Okay, so regarding to the blood, we can use serum also, not only plasma. And we don't saw large differences between serum and plasma from the same patient. And so for us, it is similar. And I would like to say that our study on the lymphoma has been done without any previous treatment of a sample and separation, for example, of sample which are older or newer, and this kind of. So it is really a study which is done with all the bad in real clinical application without checking, for example, to have a specific preparation that it is EDTA or heparin, but we have focused on the plasma EDTA samples.
Okay, thank you.
And regarding to the volume, sorry, we have worked with 500 at the end for blood, for example, 500, but it is possible to reduce by a factor of 2, about a factor of 2. And after I think it is possible to go down, but the difficulty would be the preparation of such a low volume and to have an homogeneous sample. Voilà.
Okay, thank you. And the next question is, are SOPs limited to blood and urine? I don't,
Uh,
or can it be extended to all sample types?
okay.
Oh,
So, yes. This SOP, this international recommendation, this is done for blood and urine because behind this you have a library, a database for every compound which have been measured in these conditions. But if you want, you can draw your own database for any other samples. But for example, for CSF, it is possible to do it. But you have to build a deconvolution technique which is relevant, and to be sure that your SOP is working. But it is important to develop it I think for international studies, and not only for example, for France and for a lab. So to have a kind of a decision of the different labs or country to adopt the similar preparation to make international studies and to have confidential, have a very good results when we do collaborations. Voilà.
Okay, thank you, Gilda. The last question, and I think now after we have to move forward, but the last question is from Baptiste Pantu. Did you compare VDR quantification with other methods like Kenomnics?
Yes, we are preparing an article about it. But
Okay.
yes, we compared with Kenomics, and it is really relevant.
Okay, so Baptiste, be prepared. You will find the results of your question in the next publication from Gilda and its collaborators. So thank you so much again, Gilda, for the nice presentation.
You're welcome. Thank you.
And then we have to move forward to have the next presentation from Jan. Sorry, I lost. So Jan is a PhD student in bioinformatics at Imperial College London, where he focused on applying deep learning and machine learning techniques to address challenges in NMR-based metabolomics. So thank you, Jan. And so I think you can share your screen now and
Thank you.
go ahead. Thank you so much.
Okay. Full screen. Okay, thank you. Thank you for the introduction. And today I will talk about the project about enhancing 2D J-RESRGAN spectra by using a deep learning approach. J-RESRGAN spectroscopy is one of the widely used tools to determine the molecule structures because it can separate scalar coupling from 1D into the second dimension, as shown in the pure compound spectra. But in the spectra for a real mixtures, there will be many overlapping peaks, such as the peaks around 3.8 ppm here, and notably the peaks can overlap in all directions, not on the J dimension. So the challenge is how to deconvolve or separate these overlapping peaks. There are some existing methods that are trying to fix this problem at different stages. For example, non-uniform sampling works on acquisition phase, and linear prediction works on processing phase. There are some advanced methods that perform on processed spectrum, such as fMRI and Batman, but sometimes the performance of traditional approach may not be accurate enough. And for the advanced ones, some may not be applicable for J-RES spectrum, and some may have high computational requirements and only for 1D spectrum. So our approach is to apply super resolution enhancement on J-RES spectrum. Our approach is fine-tuned based on RealResRGAN, which contains two models named generator and discriminator, shorted for G and D. And the generator is trying to generate fake data to fool the discriminator. And the discriminator is trying to classify the fake spectrum from the real ones. After training, an optimal generator will be selected, and then we can input a low-resolution image such as a cat, and we can get a super-resolution output. And we can also input a low-resolution spectrum and get a super-resolution spectrum here. And since we modified the RFMF to enhance J-RES spectrum, we call it J-RESRGAN. So in order to retrain this network, we use the simulated spectrum. And since the inputs requires pairs of high resolution and low resolution spectrum, we simulate both of them. First, we select most abundant metabolites in urine sample and use their experimental spectrum, and then linearly combine them into high-resolution spectrum for simulating mixtures. And here is a zoomed-in example. Then we apply blurring and downsampling to generate low-resolution spectrum. And here is a corresponding low-resolution spectrum. For testing data, we also use the simulated spectrum, which use similar methods as training data, but with different metabolites. We also use experimental data to test. Several J-RES experiments of different resolution are acquired by changing the number of increments, like 14 increments, 18, and 116. For each pair of low resolution and high resolution, there is a double resolution increment. Our experimental spectra include different biofluids like urine, plasma, and milk. After preparing the data, we are ready to retrain the network. In training phase, pairs of high resolution and low resolution are as input. Low resolution are fed into the generator, which will create the super resolution spectrum. And then the super resolution and high resolution are compelled to give feedbacks to the generator. Additionally, super resolution and high resolution are also evaluated to feedback the discriminator, which will try to assess the reliability of the real one and the generated one. And in the testing phase, the low resolution spectrum is as input into an optimal generator, and it will generate a corresponding super resolution output. Importantly, our J-RESRGAN introduced a novel symmetric loss function to capture the symmetry of J-RES spectrum. In order to evaluate the resolution enhancement performance, we need to find if nearby peaks are better resolved or not. To do this, we look at many pairs of nearby peaks as possible. For each detected peak, for example, this peak marked in red star, we search its nearby peaks in any directions. So the distance is measured in pixels, and then select 3 closest neighborhoods, and we get 3 peak pairs. Then we compute the resolvability score for each peak pair, and to see whether this is improved by the application of J-RESRGAN. Resolvability score is to measure the peak separation based on the height of the dip between 2 peaks. And we categorize the scores into 3 subgroups, 0.6 to 1 as well resolved, 0.2 to 0.6 as partially resolved, and below 0.2 as poorly resolved. So first we validate the J-RESRGAN on simulated spectra. Plot A shows the trend of resolvability across high resolution to low resolution, then to super resolution. Y-axis shows resolvability score. Each pixel is represented by a chiplet of blue, red, and green points joined by a line. We start in the middle with the low resolution data in red. The ideal high resolution resolvability is shown by the blue point on the left, and the result of J-RESRGAN is in green on the right. The ideal profile looks like a V, so we call it a V-plot. Obviously, plot A shows a promising V shape, and plot B shows a high correlation between high resolution and the low and the super resolution. This plot indicates J-RESRGAN is able to recover the details of ground truth from degraded low-resolution spectrum. And here are 3 examples. The first one is a well-resolved example. The up image is zoomed-in J-RES spectrum. The bottom plots are a corresponding profile along the red line in the up image. The singlet in the low resolution can be recovered to a doublet in the super resolution, and show a higher resolvability score than the ground truth. The second one is a partially resolved example. Although the resolvability score is not that high as the first one, the coupling pattern can still be recovered. The last one is a poorly resolved example. The singlet in low resolution will stay at the same in the super resolution. And here is a summary for validation on real spectrum. As we train the network on simulated urine spectrum, we validate on plasma spectrum here. From plot A, there are more than 95% pixels that show higher resolvability in super resolution than that in low resolution. Additionally, compared to the traditional experimental acquisition of high-resolution spectrum, J-RESRGAN is much more efficient because it just needs few seconds in a standard laptop. And here are 2 examples from real data. Both plots show enhanced resolution in super resolution output and recover the coupling pattern from the ground truth. And we also validate J-RESRGAN on other samples. For this V-plot, it includes 4 pairs of low resolution and the high resolution spectrum, and they are acquired in 600 macros. The majority of pixels again show an ideal V shape, and this V-plot show 1 pair of low resolution and high resolution spectrum, which are acquired in 800 macros. This example indicates J-RESRGAN can work at different magnetic fields. And we also compare the J-RESRGAN with traditional resolution boosting methods like NUS. Plot A is a V-plot by using NUS with a 15% sampling rate, and the plot B shows a V-plot by using J-RESRGAN. Both NUS and J-RESRGAN are set to increase the resolution by a factor of 2 here. And plot C compares the resolvability score obtained by NUS and J-RESRGAN. Plot D shows the difference of resolvability score compared to low resolution for both of NUS and J-RESRGAN. From this figure, we can find J-RESRGAN works better than NUS on peak deconvolution. In conclusion, firstly, J-RESRGAN demonstrates a promising performance on peak deconvolution. And compared to traditional resolution methods, J-RESRGAN is more efficient and more effective. Lastly, J-RESRGAN can work at different sample types and magnetic fields. I would like to thank to all my supervisors and co-authors, and these are 2 QR codes to access the J-RESRGAN GitHub and paper. Thanks for your attention.
Thank you, Jan, for this presentation. Please feel free to ask your question in the chat, and we have time for one question. I have one. Maybe you mentioned that you selected specific metabolites for the validation of your workflow. Do you have a specific criteria to select these metabolites, or it could be any metabolite identified?
For the data for training and testing, the metabolites I just selected by randomly.
Okay.
Yeah.
Okay, and do you expect to have the same result for all the metabolites or signals observed in the analysis?
Sorry.
So is it metabolite specific, or is it specific? The improving, is it specific to a type of metabolites, or?
No. I think this network can work on different metabolites, not on just a specific metabolites.
Okay, thank you.
Okay, yeah.
I don't see any other questions in the chat.
Yeah.
So thank you again for the presentation. We can now move to our last speaker, Marion Maravat. Marion is a biochemist specialized in NMR-Metabolomics from University of Toulouse. In 2022, she joined the Fluxomique MetaTool platform, where she works as an NMR-Metabolomics engineer. She's working on developing miniaturization of proton NMR experiments, and we are pleased to hear about this topic today. So go ahead, Marion. I think you have now the right to share your screen. Is it working? Perfect, we can see it.
Perfect. So thank you to the RFMF for the invitation. It's really an honor to be part of this webinar. Today we will present you a project that was funded by European funds in response to the COVID-19 pandemics. The goal of this project was to miniaturize our proton NMR analysis for Metabolomics. And the funds allowed us to acquire a new NMR console and microprobe. So I'm sure I don't have to convince you that NMR is very powerful. You've seen this with the previous presentation. With NMR, we can have information about structure, but here...
Excuse me, Marion, we have a problem with the sound. It's not so clear, so maybe if you turn off your camera, it will be better.
Okay.
Or if you use a microphone.
Can you hear me better?
I'm not sure.
Okay. Sorry, I don't hear anything with the cask, the headset. Can you hear me now?
Yes, we can hear you. It's still a bit the same, but maybe I think we can try to continue like that if it's still clear. Maybe if you talk slowly.
Okay. Where was I? Okay, so NMR is very powerful. We can do, here in our lab, we do especially absolute quantification and also isotopic labeling analysis. NMR has many advantages. It's highly reproducible, it's non-destructive, but as you heard my previous presenter say, it lacks sensitivity. So what happens when you have, for example, a small sample, let's say, how do you do with that? Well, you could dilute it and then do a longer experiment by accumulating more signal. But if you have a lot of sample, it is not really compatible with that configuration. The other thing you could easily do is decrease the NMR tube diameter. Is it okay? Can you hear me still?
We can hear you, but
it's really complicated. Maybe if it will appear again, we will stop the seminar and we will do it the next for next one because it's really difficult to hear you.
Okay. I don't know what to do. Because
do you want to... Est-ce que tu veux essayer le casque again?
Maybe if you try with your headset and then reconnect again. I don't know if it will work better.
Hello?
I don't know. Yes, we can hear you. It's I think it's way better. So maybe we can you can continue this way.
Oh.
We can still see your screen also, so go ahead.
Okay.
Sorry for this issue.
No, sorry, I don't know
continue.
why it was not working, but okay.
Don't worry.
So
go ahead.
I was talking about decreasing the NMR tube's diameter, and this is exactly what I did in this project. So I will put you a picture of the tubes traditionally used, 5 and 3 millimeters. So in the 5, you put around 600 microliter, in the 3 millimeters around 200. And I used the 1.7 millimeters tubes, in which you can put around 50 microliters. So which means less sample and also less solvent. So as you can imagine, these tubes are quite hard to fill. But luckily here at the lab, we have a robot which can fill the NMR tube for us.
So it is used with our standard tubes. You see the needle here, and we also have the script adapted for the small tubes and also the needles, so it can be filled fully in a fully automatized way. So these small tubes, I analyzed them in a microcryo probe that you see here. And this probe was installed on our 800 megahertz spectrometer. I analyzed different type of samples. I had synthetic urine that I made myself, freeze-dried liver, some plasma, and some cellular samples from coli and yeast. All of these samples were analyzed in different quantities to see how low we could get, and in 5 replicates. So all these analyses done on the microcryo probe, they were compared with the same analysis on our standard apparatus, which are the 3 millimeter NMR tubes in a 5 millimeter cryo probes in the 500, but also on the 600 megahertz that we have also in Toulouse. And as for the acquisition parameters, they were kept the same for all the analysis to be comparable. And also the experiments were kept quite short with 32 scans. So now we'll show you some of the results of this all these experiments. So first we have the liver extract. So you can see on the graph on the top, there is a graph with the sensitivity, which was determined with the number of peaks in the spectra with a signal to noise ratio superior to 10. And on the right, so on the sensitivity, the higher the bar is, the higher is the signal to noise in the spectra. On the right, you have how I estimated the resolution. Actually, it's the width of our standard in the sample. So actually, on this side, the higher the bar is, the lower is the resolution. So if you can see that with the microcryo probe, we have indeed a higher sensitivity, and it's also illustrated with the spectra that I put in the slide. But we have to sacrifice a little bit of resolution for this. But we are really happy with the result for the 1 milligram of dried liver, because we get a really increased sensitivity. Now for the plasma, we have the same tendency. So the microcryo probe gave us a higher sensitivity. Even for the sample containing only 12 microliters, and it's also illustrated with the spectra on the slide. Now for the cell samples, we see the same tendency, but the cell experiments still need improvement. We did some first experiment. We went below 25 microliter of supernatant for the coli sample, and it was not satisfying. So we went with 25 and up. You can see that the sensitivity is still increased with the microcryo probe, but we got really large error bar. It was because some sample had really bad chim, so it really influenced this result. We plan to do more experiment on the cells. So still on coli samples, now with the extract, we extracted some filters. The results are not as satisfying as the one we had before, but we still see on our spectra that we get more results. And actually, our goal is still a work in progress. But our goal is to completely automatize this workflow with a robotized fast filtration on filtrating plaques. So they still need some work. And I will finish with the result on the synthetic urine. So once again, the sensitivity is highly increased with the microcryo probe. This time, only 50 samples with 50 microliters were analyzed. But the urine was also used to determine the LOD. I came across this publication that described the calculation for a normalized LOD scaled to 600 megahertz, and the result is given in nanomole square roots of hertz. And the result of this calculation, I did it on the urine because it was a synthetic urine that I prepared, so I knew exactly the concentration of the metabolites in the samples. And I could use a few of the signals in the spectra to determine this LOD. And the result gives us that in the miniaturized method, we have a result of around 3 compared to the standard ones around 6. So we get a decrease of twofold. So maybe I was a bit fast with all the quantities, but here is a recap of all the quantities that we normally used in our standard protocols and the quantities we could reach. We went as low as what you can see on the slide, and we got satisfying results. This means that now when somebody comes to us with a limited sample, we can analyze them without problem. And this gives us some possible application. We can consider a multi-omics analysis when we have small samples. We can consider analyzing sample from small organism, also analyzing parts of organs, because we saw that with only 1 milligram of dried liver, we had really good results. And we could also consider doing some kinetics on small animals and some cell cultures on microplaques. And thank you for your attention. Sorry about the mic problems, and I would like to thank also my team for their support.
Thank you so much, Marion. So there is a question. Can you give us an idea of the analysis time per sample?
It was less than 10 minutes. I don't remember exactly. Yes, it was less than 10 minutes.
Okay. So and how do you explain the small difference in sensitivity between 600 megahertz and 800 megahertz with tube of identical diameters? Is the probe the main cause?
It's the field, the magnetic field.
Okay. And can you clarify the comparisons where 3 or 5 millimeters tubes with a 5 millimeters probe versus 1.7 tubes with the microcoil probe? So I'm sorry, I don't understand the question, but I think it's maybe you can read the question.
I'm not sure so in the I will try to. So we have 5 millimeter probes here, and we can use 3 millimeters tubes in them, but we cannot use 1.7 millimeters because it's too small. It's too far from the coil if you use them in this probe. So that's why we have a micro probe for these tubes. I don't know if that was the question.
Maybe Liz, you can open your mic and ask
Yes.
directly. Sorry. Huh?
Yeah, sorry, it just cut out at the beginning. I didn't understand the setup. So you're using 5mm tubes, 5mm probe for the normal tubes and the smaller tubes,
Yeah.
and then is it a microcoil or a like what is the small probe that you're using?
It's you didn't see the picture? It's a micro cryoprobe.
Micro cryoprobe. Okay.
Yes.
All right.
It has smaller diameter.
And do you have, like, we've compared 1.7 versus 3 ml, and there's just a lot of pain in filling those tubes and, you know, getting things to be pretty standardized. It seems like you're saying with the automation that it's okay.
Yes, yes. Let me go back. Yes, it was validated, the sample preparation. It's used every time we have an NMR sample to prepare, we use the robot. It works perfectly.
Okay. Cool. Thank you.
Okay.
You're welcome.
Thank you again,